We're given the vector field f and asked to determine if the vector field is conservative. If it is conservative, we want to find the function little f so that the vector field f equals the gradient of little f, meaning f of x comma y would be the potential function. And then if we're able to find the potential function, we want to use this to evaluate the line integral along the curve C of f dot differential r using the fundamental theorem of line integrals. Let's first determine if the given vector field is conservative. Because the vector field is a two-dimensional vector field, or a vector field in a plane, we use the test shown here below, where the test for a conservative vector field in a plane, given the vector field f has components p comma q, which have continuous partial derivatives over an open disk, is conservative if and only if the partial of q with respect to x equals the partial of p with respect to y. So notice for our vector field, p is equal to x squared y cubed, and q is equal to x cubed y squared. So this is conservative if the partial of q with respect to x equals the partial of p with respect to y. Well, the partial of q with respect to x is equal to the derivative of x cubed y squared with respect to x, which would be 3x squared y squared. And the partial of p with respect to y is equal to the derivative of x squared y cubed with respect to y, which would also be 3x squared y squared. So because these two partial derivatives are equal to each other, we know the given vector field is conservative. So the answer here is yes. And now let's work on determining the potential function little f of x comma y. Again, we now know that the given vector field is conservative. We want to find the potential function little f of x comma y such that the vector field f equals the gradient of little f. Remember, the gradient of little f would have components, the partial of f with respect to x comma the partial of f with respect to y, which means x squared y cubed must be equal to the partial of f with respect to x, and x cubed y squared must be equal to the partial of f with respect to y. So now we'll integrate to reconstruct the potential function f of x comma y. So integrate the x component with respect to x and the y component with respect to y. So this will give us the integral of x squared y cubed dx, and this will give us the integral of x cubed y squared dy. And now let's integrate here with respect to x, treating y as a constant. So we'd have x cubed y cubed divided by 3. This is only recovering the x part of our function f of x comma y. We could still be missing y terms as well as a constant, so we'll put plus g of y to represent a function of y as well as a constant. And now we'll integrate here with respect to y, treating x as a constant. So once again, we're going to have x cubed y cubed divided by 3. Now here we could be missing x terms as well as a constant, so we'll put plus a function of x, let's call it h of x. And now by analyzing these two antiderivatives, we should be able to reconstruct f of x comma y. In this case, it's pretty straightforward. F of x comma y, notice how these two terms are the same, is just going to be, let's write it as 1/3 x cubed y cubed plus a constant of integration, which would be, let's say, k. So going back to our first slide, we now know f of x comma y is equal to 1/3 x cubed y cubed plus k, which is already here for us. And now we want to use the potential function to evaluate the line integral along the curve C of f dot differential r, which involves the fundamental theorem of line integrals. So let's review this. If we let C be a piecewise smooth curve lying in an open region R, given by the vector function r of t, if the vector field f is continuous and conservative, then the integral along the curve C of f dot differential r equals little f, which is the potential function of x of b comma y of b minus little f of x of a comma y of a. Again, where f is the potential function of the vector field f. So this theorem is telling us that if a vector field is conservative, then the line integral between any 2 points is a difference in the values of the potential function at these 2 points regardless of the path used. So because we know the given vector field is conservative, and we now know the potential function f of x comma y, we can use this to evaluate the line integral along the curve C of f dot differential r. Before we do this though, notice how the curve is given by the vector function r of t, where x, or x of t, is equal to 2 cosine t, and y of t is equal to 2 sine t, and t is on the closed interval from 0 to pi over 4. Now applying the fundamental theorem of line integrals to evaluate this line integral, this is equal to the potential function, or little f, evaluated at x of pi over 4, comma y of pi over 4, minus f of x of 0, comma y of 0. Well, x of pi over 4 is equal to 2 cosine pi over 4, which equals 2 times square root 2 over 2, which equals square root 2, and y of pi over 4 is equal to 2 times sine pi over 4, which is also 2 times square root 2 over 2, which equals square root 2. So here we have f of square root 2, comma square root 2 minus f of x of 0, comma y of 0. Well, x of 0 is equal to 2 times cosine 0, which equals 2 times 1 or 2, and y of 0 is equal to 2 times sine 0, which equals 2 times 0, or 0. So here we have f of 2 comma 0. And now performing substitution into the potential function here, we have 1/3 times the square root of 2 cubed times the square root of 2 cubed again, minus 1/3 times 2 to the third times 0 to the third. Simplifying, we get 1/3 times 2 square root 2 times 2 square root 2, which equals 8/3, or as a decimal, this will be approximately 2.6667. I hope you found this helpful.